All right, honors stats. This is chapter 5, section 3, dealing with tree diagrams and counting techniques. Our focus points, we're going to organize outcomes in a sample space using tree diagrams. Okay, that's going to give you all the total outcomes of certain events. I did a tree diagram for you one time. Remember when we did heads and tails? And we did 3 flips and we were able to do HHH, HHT, and so on. We're going to go in a little more depth on this. The second thing we're going to do is we're going to compute the number of ordered arrangements of outcomes using permutations. With permutations, ladies and gentlemen, we are going to be using a key on your calculator, okay, which I will explain here in a moment. But a permutation is denoted by a number n, the permutation, and a number r. It's read n things permutation r times. So n is going to be the bigger number. Then we're going to do combinations. We're going to compute the number of non-ordered groupings of outcomes using combinations. That is n, c, r. Also involved with this is a factorial symbol. And then we're going to explain how counting techniques relate to probability in everyday life. So we're turning these into probabilities. Okay, so let's make sure in our calculators. Get your calculator out, put this on the video just so you know. Hopefully you have some type of the TI 84, 83, 85. If not, I'm going to have to figure out your calculator or you have to figure it out. But on the TI 84-ish, look at top left, third key down, you will see the word what? Math. Please hit that math key. It'll appear up top, math, NUM, CPX, and PRB. I want you to arrow to the right until you get to PRB. Number 2 is what? NPR. That's this one. Number 3 is NCR. That is this one. And the fourth one is factorial. That is that guy. Okay? So we'll teach you how to do it. The N means you have to type a number in first. Then you go to that keystrokes that I gave you, then you hit the NPR, and then you hit another number. So when we get to the examples here, I'll explain it using a calculator, but you won't have to compute these by hand. Everybody knows this formula. The probability of event A is the number of outcomes favorable to the event over the number of outcomes in the sample space. That's the total number of outcomes. All right, so we're going to be dealing with finding this first, okay? The total number of outcomes. First is our multiplication principle, okay? The multiplication rule of counting. Consider a series of events, E1 through EM. E1 meaning the first event, E2 would be the second, and so on. N1 is the number of possible outcomes for event 1, N2 would be the number of possible outcomes for event 2, etc. What you do is you're going to multiply each of those outcomes. So here's a great example. I have 10 t-shirts. I have 5 pairs of jeans. And I have 3 pairs of shoes. Assuming that all of these match, it doesn't matter what t-shirt I put on, what jeans I put on, what shoes, I will look good. It will match. My question is, how many total outfits could I put on? Ladies and gentlemen, it's the multiplication principle. You simply multiply the number of possible outcomes for each event. This gives me 150. Ladies and gentlemen, there are 150 different t-shirt, jean, shoe outfits I could put on. Okay? Multiplication principle. So the 150, like I said, is the total number of outcomes. If I was going to make a probability question, which I'm not, and I ask for about a specific outfit, what is the probability, how many outfits could I have with purple shirts? Okay, depending how many purple shirts and whatever, it would be whatever number over what? 150. Okay, that's your total number. So their example. Jacqueline is in a nursing program, is required to take courses in psychology, physiology next semester. She also wants to take Spanish. There are 2 sections of psychology, which I'll denote by PS. There are 2 sections of physiology, which I'm going to denote by PH. And there are 3 sections of Spanish, which I'll denote by SP. How many different class schedules can she choose from? So, if there's 2 psychologies, there are 2 physiologies, and there are 3 Spanishes, there are 12 different course schedules she could take. Multiplication principle. Now, let's take a look at a tree diagram to prove this particular fact, okay? Since they did psychology first, that was PH, right? How many PH classes are there? There were 2 of them. 1, 2. We'll call this PH1, first class, PH2, second class she could take. Then there was how many psychology? 2. I call that PS. So that's PS1, PS2, oops, put the S, sorry, PS2. And off of here, she could take PS1 or she could take the PS2. And lastly, there were what classes? Spanish, and there were 3. So this is going to be Spanish 1. Off of here is Spanish possible class 2, Spanish 3. Off of here would be Spanish 1, Spanish 2, or she could take Spanish class 3. Off of here, Spanish 1, Spanish 2, or Spanish 3. And off of here, Spanish 1, Spanish 2, or Spanish 3. If you count the last column of outcomes, it should equal the total number of outcomes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And if you had to write them out, you read them this way. Ladies and gentlemen, she could take the PH1 class, the PS1, and the SP1. That is one of the 12 scenarios. Or, let me change my color here. She can take the PH1, the PS1 with the Spanish 2. That is scenario number 2. Or PH1, PS1 with Spanish 3. And you can continue on. So if I wanted you to write all individual outcomes, you could definitely do that as well. Okay? Tree diagram. Okay, let's throw one out there. Let's say I ask you to roll a die first and then flip a coin. Let's do the principle first. Let's do the multiplication principle. How many outcomes of rolling a die? 6. How many of a coin? 2. What's 6 times 2? 12. Here's the coin. That's the die. 1, 2, 3, 4, 5, 6. You can get a 1, a 2, a 3, a 4, a 5, and a 6. Sorry, I'm doing this tree diagram up and down. And then everyone, you can flip a coin and get a head or a what? Off of the 2, you can get a head or a tail. Off the 3, head or tail. Off the 4, head or tail. Off the 5, head or tail. Off the 6, head or tail. So what are some possible answers? 1 head, 1 tail. 2 head, 2 tail. 3 head, 3 tail. You got it? 12 of them. Tree diagrams, guys. Now starting counting principles. Ladies and gentlemen, we're going to be dealing with a factorial notation, The best factorial to look at right now, or I should say the formula to look at, is this guy right here. N factorial, if you look at that, whatever number here, it starts with that same number, and then it goes 1 less times, and then 2 less times, and so on and so forth. So for example, 8 factorial actually means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And you get a big old number. Well, guess what? I don't want you to take your calculator and plug all those numbers in, because I want to be able to give you 20 factorial. without you being scared. So guess what? My calculator's out. I'm going to type in an 8. I'm going to go to that math key. I'm going to scroll over to PRB, and I'll see the number 4 has a factorial. I'll hit a number 4. On my calculator has 8 factorial. I hit enter, and it spits out 40,320. Done. There are 2 special factorials that you need to see. First one is 1 factorial. Ladies, 1 factorial, ladies and gentlemen, is what? 1. And the weird one, what is 0 factorial? 1. I'll explain that in a moment. Let's do a couple of examples. Okay, we're going to do a hard one first. I have 34 people in here right now. 34 people. We have to go to a presentation in the gym, and I want to line you guys up. How many different ways can I line 34 people up? Well, how many people do I have to choose to sit in that first spot? 34. Once I have somebody there, how many people are left for the second spot? All the way down to what? 1. So that is 34 factorial by definition. Guys, if I plug 34 factorial into my calculator, 34 math, scroll over, hit the factorial 4, guys, it spits out 2.95 with 36 zeros after it. 36 zeros. That's 2.5 gajillion, badillion. I don't even know the number. It's that large. But it's you sitting in front of me. There's no more. So I can actually put you guys in a line more ways than you can even imagine that number. Okay? So let's talk about another example. You, including yourself, your parents say, we'll let you and 9 of your friends, so a total of 10 people, all right? Let's do this. You have to choose 10 friends to go with you to a park on your birthday. How many different ways can you choose those 10 friends? No, you have 10, there's 10, and then 9, then 8, so 10 factorial. Okay. Now, I didn't give you a bank of friends, okay? So you're calling them up. So you have how many people to choose to call first? 10. Once you call that friend, then you have how many people left? 9. Once you call that friend, how many you have left? 8. And each time you call a person, you're saying, hey, let's go to Disney for my birthday. See what I'm saying? So that's 10 factorial. 10 math, scroll over, 4 factorial. That is 3,628,800 ways. Guys, 3.6 million ways you can call 10 of your friends and ask them to go to a party with you or go to Disney with you. Crazy. Now let's see how smart you guys are. Okay, I've talked about lining up on a line. How many ways can 10 people line up on a line? 10 factorial. How many ways you use? What if I said this? How many ways can you plant? I started to write the word flower first. Can you plant flowers in a circular garden? All right, I'm going to pause the video here while you guys think. Oh, I guess I got to give you a number of flowers. 8 flowers. How many ways can you plant 8 flowers in a circular garden? A circular permutation is always 1 less factorial. The answer to this is 7 factorial, which is 5,040. And basically what happens if I make a circle, what you have to do is you have to take one of the flowers first and actually plant it. Once that flower is planted, we now can choose the next 7 or excuse me, the next one where we have 7 choices. Okay? So if there's a circular permutation, okay, ready? How many ways can 10 people line up in a line? 10 factorial. Line up in a line. 10 factorial. How many ways can 10 people go into a circle? 9 factorial. Commit it to memory. That's a circular permutation. And now, ladies and gentlemen, permutation itself. It is denoted by NPR. This thing. I've never seen this thing before in my life with a comma. Obviously, you look at your calculator and it has NPR. That is N things taken R times. N things taken R times. Okay? So, for a permutation, order is important. Order is important. Now, I am giving you permission to use a calculator. You see, if you didn't use a calculator and you were solving 10p6, if you look at the formula right here, it's the big number factorial, and then I have to subtract those factorial, and then I have to go 10 times 9 times 8 times 7 times 6 times 5 times 4 factorial, and the 4 factorials will cancel, and I got to pull my calculator out and type 10 times 9 times 8 times 7 times 6 times 5. I don't want to do that. I'm letting you use your what? You simply type in a 10, go to math, scroll over to probability, hit the P key, hit the 6 key, hit enter. So I'm going to do that. 10, math, scroll over, hit the P key, which is the 2 key, hit the 6 key, hit enter, and it spits out 151,200. Okay. So right now, you know what a P is, a permutation. All you know is the order is important, and you know how to type it into your calculator. Give me a moment with combination, and I'll come back to exactly how these guys work, okay? Here's a combination, ladies and gentlemen. Combination. Order is what? If one of them is order is important, what's for combination? Not. Order is not important. Not. Repeat that. Not. A combination is always smaller, okay? So if I was going to do 10C6, look at the formula. It says I want the bigger number on top factorial, I want the smaller number on bottom factorial, and I want the subtraction of them factorial. Okay? A little more work. Do you agree? But what am I letting you do? Type it into your calculator. So I'm going to type in 10. I'm going to go to math. I'm going to scroll over to C this time, 3. I'm going to hit a 6. I'm going to hit enter. And it gives me 210. Combinations are much smaller than permutations, just so you know. They're much smaller. Why? Because order's not important. So I put everything here, just so you guys know. Oops. Let me get the mirroring going. This is where it's all going to be at with what I have written here. Hopefully this will help you with permutation and combination. Mm-hmm. This isn't in your notes, so okay, ready? Permutation, I told you, order is important. Permutation, order is important. So, arranging people, digits, numbers, letters, and colors. Guys, if I just give you a list of colors and I tell you just to choose colors, that's a permutation. They mean nothing to you, okay? The order is important on how they're chosen, okay? Combination order is not important. Selection of a menu, food, clothes, subjects, teams. This next is the most important. I think this is monstrous. If you can understand these two, ready? If you're picking a team captain, a pitcher, and a shortstop from a group, obviously this is your baseball team, okay? So I said team captain, so whoever gets chosen first is the what? Team captain. Who gets chosen second is the what? The pitcher. Who gets chosen third is the... See, that order is important because if you choose them in a different order, you're going to have a different pitcher, a different shortstop, and a different captain. But look over here. You're picking 3 team members. I need 3 outfielders. I don't care if they're right field, left field. I need 3 outfielders. So if I choose you, what are you? Outfielder. If I choose the next person, what is that person? What's the next person? Beautiful. Let's do a restaurant. A restaurant. This is a great scenario as well. I need to hire a maitre d'. I need to hire a front desk person, and I need to hire a server. Order is important because if I choose you first, you're the maitre d'. If I choose you second, you're the front desk person. If I choose you third, you are the server. But then I say, I need to hire 3 dishwashers. First person is a dishwasher. Second person is a dishwasher. Third person is a dishwasher. The order is not important. They're all dishwashers. But in the first one, the order is important. First, second, third place winners. You see, if you choose the first place winner, they're getting the biggest prize. Second place is getting the next. So the order is important on how you choose them. But if you're just picking 3 winners, they're all getting the same prize. I don't care if you pick me last. I'm still getting the same prize. Okay? So, you have factorial. You have the multiplication principle. I gave you a great example of those about the clothes and then the classes that we choose. Factorial, people standing in a line. I gave you circular permutation. It's 1 less. And now permutations and combinations. So if I say, we'll give you 1 example of each. Now I'll get specific. For mu alpha theta, I have 20 senior members, and I must choose the president, the vice president, the secretary, and the treasurer. Tell me what that answer is going to be using C or P. That is 20 people, permutation 4. The order is important because the president is different than the vice president, which is different than the secretary, which is different than the treasurer. Obviously, use your what? Calculator. Let's change scenario. Ladies and gentlemen, I have 20 senior mu alpha theta members standing in front of me, and I need to choose 4 tutors. That's a what? That's a combination because what are they all? They are all tutors, and the order of me choosing them is not important. If I'm chosen first, I'm a tutor. If I'm chosen fourth, I'm a tutor. If I'm chosen third, I'm a tutor. And lastly, lottery. Lottery. So, in Florida, the lottery numbers, there are 56 ping pong balls that go in this thing that blows them around. And they choose 6 numbers. You have a 50-50 shot. Do you think this is a C or P question? Let me give you a hint. You walk in and you say to the person who's typing I want a ticket with these numbers on it. 1, 2, 3, 4, 5, and 6. You're going to get a card printed out with what? 1, 2, 3, 4, 5, 6. You walk in and say, okay, I want a 5. And then next, can you type in 1? And after that, type in a 3. And then type in a 6 for me. And then type in a 2. What card's going to print out? 1, 2, 3, 4, 5, 6. Ladies and gentlemen, this is a combination. So, The lottery, and if you think about this, let me type this in for you. 56 math, combination 6. That is 32,468,436. That's as many individual tickets that can be printed out. 1, 2, 3, 4, 5, 6, all the way up to 50, 51, 52, 53, 54, 55, 56. Or I should say 51 to 56. There are no others. This is every combination of ticket that can be printed out. So if you think about it, guys, if the lotto sometimes is $500 million, $500 million. If you're rich and you have $32 million in the bank, well, obviously 32,468, could you feasibly buy every single ticket and you would be guaranteed to win?
Yeah.
Oh, yes, you would be. Number one, it can't happen because a machine cannot print out 32 million tickets. It can't happen. Okay? Plus another problem would be, what if somebody else won? You'd have to split the money. But scenario, if nobody else won and you bought 32.468 million tickets, you would actually win the $500 million because that's as many tickets that can be printed. Okay? So ladies and gentlemen, this is chapter 5.3. As we do the homework, you're going to get better and better at what type of problem is permutation and what type of problem uses combination. Multiplication principle are very straightforward, and factorial are very straightforward.